In this video from ITFreeTraining, I will look at how a node on an IP6 network can be automatically configured. IP6 offers improvements over IP4, allowing a node to configure itself without the need to deploy any additional hardware or software on the network. There are fundamentally two different ways that a node on the network can be configured to use IP6. The first method is called Stateful. This is when configuration is performed using a DHCP server. This kind of configuration is common in IP4. Stateful configuration is also considered to have been performed when the node has been configured manually. Using stateful configuration requires the administrator to either configure a DHCP server on the network or manually configure the node. One of the objectives of IP6 was to make it possible for nodes to automatically configure themselves without the need for the administrator to have to do anything. IP6 adds the feature Stateless. This is also known as Slack. One of the main objectives of IP6 was to remove the need to use broadcasts. Thus, Stateless uses neighbor discovery to configure a node, eliminating the need for broadcasts. The advantage of Stateless is that no DHCP server is required to be installed and configured on the network. The disadvantage of Stateless is that it only provides basic configuration. This is enough to get the node up on the network and working, but does not support advanced configuration, like booting from the network. In order to do this, a DHCP server can be set up to provide additional configuration. So Stateless can be used by itself or with a DHCP server on the network to configure clients. In the DHCP course, I will go through how to configure a DHCP server for use on the IP6 network. For this video, I will only look at how to configure stateless configuration. To start with, I will first look at the link local address since it is required for stateless configuration. The link local address is used for local network access only. It is not routable on the Internet or other networks. A link local address is assigned to all network interfaces. The link local address will also be present even if an IP6 address is configured. To demonstrate this, I will open a command prompt and run the command ipconfig. This will show the network configuration for this computer. This computer has been isolated, so there are no other devices on the same network that it is located on. Thus, this computer will not be able to obtain any configuration other than what is supplied by default. This computer has two network cards. At the top, notice the link local address that has been configured automatically for this network card. Later in the video, you will notice that this address is still present, even when a functioning IP6 address has been configured. Notice that below this is the link local address for the second network adapter. This address is different from the one above it. Each network adapter will have a different address. Let's have a closer look at each address. You will be able to easily identify a link local address because it will always start with FE80. Following this is 54 bits of zeros. The last part of the address is the interface ID, which is random or based on the MAC address. Originally in Windows XP, the link local address was calculated using the MAC address. Since it was calculated from the MAC address, it was possible, by using the IP address, to work out the MAC address. This raised a number of privacy concerns, so after Windows XP, this was changed to be random. On Linux, depending on the distribution, the link local address is generally calculated off the MAC address. When a link local address is first assigned to a network interface, a check is done on the network to make sure it is unique. This ensures that this computer is the only computer or device on that network that has that link local address. Let's have a closer look at this process. When a link local address is created, it goes through a number of different states. The first state is tentative. During this stage, the address is checked to make sure it is unique on the network. Once this check has been performed, the address becomes preferred. Preferred simply means the address is considered valid for receiving and sending on. When the IP address reaches the end of its life, it becomes deprecated. Deprecated addresses should not be used for new connections, but old connections can still use them. After this, the address becomes invalid and can no longer be used. To have a look at the different states, I will open a command prompt and run the command ipconfig with the /all parameter. This will show more detail than just running ipconfig by itself. Once the command is run, I will scroll up to the top to the first network adapter. Notice next to the IP link local address is the text preferred. This means this address is the preferred address to be used for new connections. The tentative state is for such a short period of time, less than a second, so it is unlikely you will see tentative state. On this computer, there is no deprecated IP address that I can see using ipconfig. To see some, I will run the command NetSH. Once NetSH is running, I will run the command Interface IPv6 to take me to the IP6 interface. From here, I will run the command show address. This will show all the IP6 addresses on the computer. Notice that one of the addresses has the title DAD state. DAD stands for duplicate address detection. Notice it has the state of deprecated. This address can still be used. However, it is recommended that new connections are not made using this address. Only existing connections should use this address. Notice to the right of this is the title valid life, which is configured to infinite. You will find that most addresses are configured to infinite. It is possible to configure a value for this. If this value is configured, the address will change to deprecated once the time period expires. You can see how an address can go through different states during its life cycle. So the question is, how does all this work to configure a valid IP6 address? As we have learned, a computer will allocate itself a link local address. To ensure that the address is not already in use, it will send a message to the address that it is trying to use. Consider in this network there is one other computer which has the same link local address. In this example, I have used simple link local addresses. However, in the real world, these addresses will be more complicated than these. To check to see if the address is not in use, the computer will send a message using ICMP to the address that it is trying to use. Notice that the source address is unspecified, since the computer does not have an address as yet that it can use. If there is a node on the network that is using that address, the node will respond back using multicast that the address is in use. Multicast will need to be used because the computer does not have an address that it can use as yet. The multicast address it will use is all nodes, which is the closest thing to broadcast that you can get in an IP6 network. If there is a duplicated address, it is up to the host to choose another link local address. So let's look at the next step in obtaining a fully functioning IP6 address. On this network there are two computers and one router. The router and one of the computers has a global unicast address that they can use to access the Internet. The computer on the left will use Stateless Autoconfiguration to configure an address. Periodically, the router will send out a router advertisement, or RA. However, if the client requires it sooner than the next advertisement, the client can send a router solicitation message, or RS, on the network. In this example, the computer has started up, allocated itself a link local address, but has not received any router advertisements. Since it has a valid link local address, the computer can send a message on the network using its link local address as the source. Notice that the destination address is a multicast address. This is the multicast address for all routers on the local network. For this reason, even though the computer does not know the address of any routers on the network, sending the message to this multicast address will ensure that the traffic will be sent to only routers on the network. On this network, the other computer will not receive the message. Only the router will receive the message. The router will then respond back with a router advertisement directly to the computer since it now knows its link local address. You can see that this was all done without the need to use a broadcast address, something that is not possible on IP4 networks. Next, I will have a look at how the client uses the router advertisement to configure an address. The router advertisement message contains a lot of configuration information, like the default gateway address for the network, but most importantly, contains the network prefix for the network. This is what is used to configure an IP address. If I have a look at the format of a global unicast address, notice the first 64 bits are the network prefix, and the last 64 bits are the interface ID. The router advertisement contains the network prefix, and, in the case of Windows, the interface ID is random. This allows the computer to configure itself a global unicast address that is usable on the Internet. This is all done without the need for a DHCP server. To finish this video, I will perform a quick summary of how Stateless can be used to configure a computer on the network. Consider that there is a computer and a router on the network. The first step is the computer configures a link local address to use on the local network and checks the network to make sure that another node on the network is not using the same address. The next step is the computer will send a route solicitation message on the network using multicast that will go to all routers on the network. The router will then respond with a router advertisement that contains information about the network, for example, the network prefix and default gateway. The last step is the computer uses this information to configure the computer address and gateway. This is all done without a DHCP server. It should also be pointed out that no DNS servers are configured using Stateless. For additional settings like these, a DHCP server is required, which works with the Stateless to configure additional settings. Remember also that the router sends out regular interval router advertisements. Using this information, computers on the network can change their configuration. For example, if a router needs to be added to the network to replace an existing router, the router advertisements could be used to direct the computers on the network to use a new router rather than the old router. Well, that's it for IP6 Autoconfiguration. I hope you found this video useful and hope to see you in other videos from us. Until then, I would like to thank you for watching.